We're still looking at this A2 paper from CCEA, Fields and Their Applications from June 2011, and we're looking at question 4, which is the electromagnetism question. So a wire is suspended in the magnetic field between two identical magnets so that it is perpendicular to the magnetic field direction. The wire is suspended so that it cannot move, and the shaded face is the north pole of each magnet. The two magnets are placed on electronic scales, and the wire is attached to a variable power supply unit and an ammeter. The reading on the scales is adjusted to 0. So this is our setup. As you can see, we've got a basic circuit. We've got a wire that's running through the gap between two magnets. We've got a circuit that will send current in a clockwise loop here. We've got something that we can vary the current with, something we can measure it with, and something that we can turn it on and off with. So we've got a magnet either side, and we've got a field running across past the wire. The switch S is then closed. On figure 4.1, carefully draw an arrow to indicate the direction of the force now experienced by the wire. Remember, the shaded face of each magnet is the north pole, so this is the important bit. And we're told that the shaded face is the pole, the north. So if the right hand side of the power pack is positive there, the long end of the symbol, then we've got this clockwise current. We've also got a north pole on the shaded face there. That tells us the field will be going across to the right. So the field's going across like that. And we can use Fleming's left-hand rule to establish what's going on here. If we've got current heading down, field going across, we end up with our thumb pointing up. And so the force on this would be an upwards force, just using Fleming's left-hand rule. Now, by considering Newton's third law, state and explain the effect of this force on the reading on the electronic scales. So we have to draw what we've got here. We've got a wire between two magnetic poles, and we're interested in this reading on the scales. So the wire is sitting between the poles of the magnet. If the wire is pushed up, then the magnets are going to be pushed down, and that will push down on the scales and therefore create an increase in the reading. So the wire is pushed up, the magnets are pushed down by Newton's third law, and that means the reading would increase. The change in the scale reading from 0 grams when different currents were passed through is given in the table. The average force acting on the magnets is going to be related to this current. So we've got these scale readings that come in, and they can then be used to work out what we call the average force. State how it is possible to obtain two scale readings for each current using the arrangement. Okay, so there are two readings here. What's the story about the two readings? Well, you can see that one of them is positive and one of them is negative. So this whole second column are all negative, and that must be the reading in the balance going the other way, and so that must be something like, for example, reversing the current. Or you could turn the magnets round and keep the current the same way, but it's easiest in that setup to reverse the current. So what about this? Calculate this average force. So we need to use W equals mg, and it says you should use the value from the physical constant from the data sheet. So you're using basically 9.81 here to be G, and that gives you 0.01256, and two 3 significant figures, that's 0.0126, and that would go in the area down below here, not necessarily, you would fill that in down here rather than where I have drawn it there. Okay, So spreadsheet software was used to analyse the results from the table, and we end up with this graph of force versus the current. Use the information in figure 4.2 to determine the force produced by a current of 4 amps. So we need to look 4 amps up on the current axis, and we need to zip that across from the graph line to the force axis, and you can see that corresponds to a force of 0.01 of a newton. And so from the graph we can figure it out to be 0.01 of a newton. Take that up, take it across, record the value. Given that the length of the wire in the magnetic field was 0.12 of a meter, calculate the magnetic flux density between the magnets. Well, this is F equals BIL because the BIL equation works when I is perpendicular to B. And that means that B is F over IL, and so F was 0.01 of a newton when I was 4, just F that value, and I is that value. So just filling those in, and then we put in the L value from the question. Stick that through a calculator and we get 0.02083 repeating, which we can write as 0.021 of a Tesla. And that's that.